All right, so in our notes for week 8, we had information about different kinds of collisions. And we need to add this little piece of information, this extra set of equations to our notes. Usually we do this in lab so that I can show you and demonstrate for you the kind of collision that we're talking about. But I want you to envision one of two scenarios. The first one that you can envision is that you're sitting at a stoplight and somebody drives up behind you texting and smashes into the back of the car. Now, this isn't a very warm and fuzzy thing to think about, but what would happen is you would shoot out into the intersection, but they would continue to move forward behind you, not connected at all. A maybe more fun application of this would be when you're shooting pool. And in this case, the first ball would be the white ball, and the second ball would be the ball that you're trying to hit into the pocket. And after the collision, the white ball, the cue ball, is going to continue to move forward, but the colored ball is going to move forward also, not connected to each other. They don't stick together at all. So I usually refer to this as a perfectly elastic fender bender. And there is a set of equations that you can use specifically for this scenario. Now, I'm working with a new stylus pen here, and it's being a bit of a pain in the butt. So bear with me a little bit here. What we have is mass of the first ball, and it's going to have a mass. That's the white one. Mass of the second ball, and it's going to have a mass. The masses aren't going to change on the other side. So whatever they are, they are. But I have velocity of the first ball, and then it says I for initial, versus velocity of the first ball, final. So it's going to change speeds. Since it's going to give some of its energy to the other ball, it's going to slow down. The second ball starts out at rest. So I've got that one all set up at 0. And then the velocity of the second ball after the collision is going to come from one of these two little equations I'm about to give you. All right, so taking our momentum equations and our kinetic energy equations and doing a whole bunch of algebra and substitution, here's what we come up with. We come up with, whoops, hang on one sec, I just touched something on my computer I wasn't supposed to touch. We come up with the following equations. The velocity of the first ball at the end is going to be equal to the difference in mass between the first ball and the second ball divided by the total mass of the first ball and the second ball. And then multiply that, this is a step that people lose a lot, by the velocity that the first ball had before the collision. So we're looking at the difference in mass divided by the total mass times the initial velocity from the first ball, because the first ball is the only one that had energy going into it. Now, compare that to, let's look at the velocity of the second ball at the end. This equation is going to look quite a bit different. It's 2 times the mass of the first ball divided by the total mass times, now, still the velocity of the first ball initially. Because again, the second ball didn't have any velocity. It didn't have any energy to put into the collision. All right, and what we'll find is at the beginning, the big vector was all ball 1. And at the end, there's a little bit that's ball 1 and a little bit that's ball 2. Okay, so I know that I turned sideways when I wrote here, and I'm sorry. I'm still trying to figure out how to keep my arm off my keyboard while I do this, because I typically do not record videos on my laptop. I typically record videos on the big monitor in the lab. I will get used to this and figure this out in the next couple days, but now you've got those two equations to work with. You're going to need these equations to do number 21 in your homework. You're also going to run into them on your exam. So make sure that you add them to your notes and that you have them available to you.